Hello. So today is week 12. Week 12 is the last final week. And what we're going to see today mainly sequence models and encoder-decoder architectures, right? And we will see some questions related to sequence models and encoder-decoder architectures. And eventually, after going through all the questions, I'm going to briefly talk about the self-attention uh, architecture, right? Multi-head attention, which is the basis of uh, our large language models. And we'll expand it slowly. So we will first see the attention block, first see some details of the attention block, and then we will see some details, uh, see the whole uh, broad architecture for GPT-2, right? And explain every block entities, right? And yeah, uh, go into some details about how attention works and what it tries to do, how you train it, how you generate data for it, and so on. So first of all, of course, we will start off with some questions, assignment type questions, and then we will see. I will briefly explain the uh, transformer architecture, multi-head attention, and yeah, and then we'll see where to do from there, right? Okay, so we'll start off with some questions. First question uh, is about sequence models. Like I said, this week is about sequence models. It is about encoder and decoder architectures. So given the first few words of a sentence, you have to predict the next word for like a complete task. Which of the following should be the output at every time step, right? So the output, the next letter, the next word, probability of some word, vocabulary, probability distribution, right? So yeah, so we'll do it. We'll do the questions in the same way that I always do the questions, which is that I will explain the question and then give some time for to answer, and then explain the solution, right? So I'll give like a minute for everyone to answer. This should be fairly straightforward based on everything that we have done throughout the course, right? Based on everything that we have looked at throughout the course. Yeah, so some answered option D. So option D is in fact the correct option. Right? What we want to do is predict the probability distribution over the entire vocabulary, and this is exactly what is done as well in the uh, current. I mean, in a very broad, general manner of speaking, this is what is done in the current uh, architecture of large language models, right? Essentially, what you do is um, generate this probability distribution and then you sample from it, right? And usually the probability distribution will be extremely skewed, right? Which means that certain word will have extremely high probability and everything else will have low probability. So you can get some kind of sort of pseudo deterministic uh, output if you choose like the word with maximum probability. Instead, what people like to do is that you sample from the probability distribution based on the distribution, right? And then you have typically you have this parameter called temperature, which you can adjust, right? So if you increase the so-called temperature, essentially what you do is in the softmax calculation, when you put e to the power of x, right? So you do e to the power of x by t, right? And then in the denominator you add e to the power of x, right? For all of the possible possible words, right? So if you increase the temperature, then your distribution becomes more flattened and you get a more probabilistic output. It's a little bit more random. So this is a trick that people sometimes use because you want the model to be able to generate kind of surprising results as well, right? So you don't want it to be completely deterministic in what it generates because then kind of loses some of its quality. So yeah, one thing of that is to say that we do in fact try to generate probability distribution over the vocabulary at every time step, right? And based on the probability distribution, you sample something, and that whatever you sample and you get out of it, that is your prediction for the next time step, right? So that's it. Now we have sequence models, previous distribution. So of course, sequence models, anything. Sequence models can be anything, right? It's just a matter of how you compute uh, the final predictions. So sequence models can be transformer architectures, which is what is currently being used everywhere, or they can be recurrent neural networks, which was the old method, right? Which was LSTM, GRE stuff. So the question here is, in the previous question, we had certain sequence model, and if you consider, for example, RNN architecture, right? So if you have an RNN architecture, how does it take into account the word at any time step depends on a few words preceding it, right? So of course, what you want to predict at any time step should depend on what has already been said or what has already been recorded. So the question is, uh, how does it map this relationship, right? Once again, this is like a very basic question, right? If you're aware of the RNN architecture, it should be very straightforward to answer this, right? Especially based on what we had previous week's discussion, which was centered on RNN. Okay, so I have pasted the today's agenda chat. Whoever has joined recently can check it out. Okay, I just give 1 more minute and then we will discuss the solution to this problem. Okay, so didn't see any answers, but yeah. So if you recall the discussion about RNNs, right? You remember that RNNs had this history hidden state variable, right, which was uh, affected by the history as well as the current event, right? You had this h of t. T is the time step where h of t would be equal to w times h of t minus 1 plus u times x of t, something like that, right? And that history hidden layer basically accounts for the past relationship, right? And uh, yeah, so you know, recurrent connections and state is actually the way that this RNN architecture uh, kind of remembers what had happened, right? And this is slightly different from the transformer, right? Because in a transformer, for example, you give a bunch of inputs, right? You give like a history, which is typically called as context length, right? So you give that many inputs and you tell it to predict the next word, right? So you have give it n context length, which means that you give it n inputs. Then you try to predict the next word, right? Which is quite different from the way in RNN works, where as the history is kind of implicitly uh, held by this hidden layer uh, activations, right? Hidden layer state. So, like I said, so this entire part basically corresponds to the history, right? And how does but that's well and good, but what we want to know is how does the prediction at this time step take account for that history. The answer is that comes from the state, right? So there is this state which has information flowing into it from the uh, past time steps, right? And it accounts for what has happened in the past and then predicts something, predicts the current world and whatever it has to predict. So in RNN, basically, the current connections and state uh, tell you what is the history term, what is the relationship with past inputs. In transformers, it is a little different because you give you give it the context, right? So that's that. So we have finally in the given island model. So here so this is an island model, right? And you are basically trying to predict the next word given the sequence of inputs, right? So when you start, you're trying to predict I. When you give I, you're trying to predict and so on and so forth, right? And this is this is very similar to, in fact, it is exactly identical to the way transformers also work, right? Because uh, they also kind of generate the it is identical to the way transformers work in inferred situations, right? When you are trying to infer uh, what you're trying to generate stuff in a regressive manner, right? Uh, but yeah, so basically we have this output, and question here is again very simple, which is that we use softmax here to express this probability, right? Probability, which is the probability of some output, right? Given everything, given everything. The question is why do we use softmax, right? And once again, this should be it should be very straightforward. And say it just like that because we just have seen that almost identical questions earlier as well. Uh, yeah, so because output is a probability distribution, obviously you need softmax, right? Because softmax gives you a probability distribution, right? So as I said, uh, fairly straightforward, right? Because remember, we are trying to predict the probability distribution over the vocabulary of words, right? So that's exactly what you want, and because that is what you want, you have to generate probability distribution at the output, which person the softmax. Right. So okay, let's move to the next problem. So here we have again the same kind of setup, right? The question is what do these what how are these words encoded at the input side? How how are the output or rather targets encoded, right? So the question is about encoding of input words and target words, right? And once again, this remember the discussion from week 9, I think, based on but the discussion from week 9 we have been discussing up until now, then should be fairly straightforward once again, exactly what is supposed to happen, right? Even the kind of some example that we have gone through last week, right? Even that we remember should, should figure out what uh, what is going on over here. Okay, so mm, so here it's the thing. So first of all, on the output side, we are looking at targets or label words, and obviously at the output side, this is going to be one hot encoded, right? Because we're trying to classify something, right? So output will obviously be one hot encoded. The question is what is the output going to be like? And typically, the most common setup in these kind of scenarios, right, where we have these RNN architectures, is that you have the input as an embedding, right? So you take an embedding as an input, and you have this RNN, then RNN predicts something, and based on that RNN prediction, you based on the RNN output, you generate uh, the probability distribution which you try to map with the one hot uh, target encoded targets. Right? So that's how that's how you normally do this. Of late, things have shifted a little bit in the sense that so previously the consensus was that you don't really train the embeddings part of your network, right? So you take these like pre-trained embeddings, right? Like something like what we use in like the previous week when I discussed the example of sentiment analysis. We use this Wiki 250, Wiki 500 kind of pre-trained embeddings, right? And that used to be basically the consensus way to do this kind of architectures, right, or models. But things have changed a little bit. So nowadays, what people do is that typically you include the embedding layer also as part of your network, right? So you have a embedding layer in between, which embeds your input, and then that embedding input goes into the RNN, and then RNN generates an output. So technically, uh, in recent times, option A is also increasingly becoming more and more popular, right? So you have one hard encoded at the input, then you have an embedding layer that generates your embedding that goes into the RNN or transform whatever, and then finally you have an output which is a probability distribution over the vocabulary, which you compare with one hard encoded uh, targets, right? So uh, since this question is kind of old, we come with this option C, right? Like I said, this was the most common approach to do these kind of things, but increasingly option A is have input and output both as one but encoded uh, values. This has become in fact more and more popular because essentially when you train for extremely large models, what happens is that it gets a very efficient or effective uh, learning of the embedding model, right? You train the embedding alongside the network, it works. It's like it works somewhat better than taking a pre-trained embedding training based on that, right? And yeah, so that's how it is these days, right? And we will see, in fact, we will see this in the GPT-2 architecture discussion later, right? Because in GPT-2 and later versions, and in fact, all of the large language models, they do exactly this, right? So they include the embedding layer as part of the network, and they train it alongside the network. And in GPT-2, something additional that they also did was that they made the embedding layer and final unembedding layer, de-embedding layer, as as the same thing, right? So they tied the weights. So you had an embedding layer in the input side, and you had a projection layer that projects your embedding into the whole vocabulary size, right? So they made the projection weight at the output as the transpose of the embedding filter, right? Which allowed them to reduce somewhat the number of parameters that they had in mind. Right. So next we have encoder-decoder models. So this is very important also, especially it is increasingly more important with the current architectures. In fact, all of these models are kind of fall into this encoder-decoder paradigm, right? Which we have ChatGPT, GPT-2, GPT-3, so on and so forth. Uh, Models, they're typically called as decoder-only models because essentially they don't have really an encoder step, right? They just continuously decode values, so they're called decoder only. Whereas there are some models like BERT, which is a proper encoder-decoder model. And typically, when the models that are specialized for language translation, so going from one language to another language, those are also typically encoder-decoder. They need both, right? So they need the encoding to be completed. They need a complete encoding of the source language, right? And then they do a complete decoding on the target language based on what the source language encoding has been developed, right? Generated. So, with that background, uh, here is this question is a little different. Here, the encoder decoder part of it is what is typically called as multimodal, right? Because you have two modalities, right? So you have an image captioning problem. Basically, uh, you have an image, and you want to generate something about that image, right? So you want to make a descriptive statement about that image. So the question here is that the image is encoded by an abstract. So basically, you have a pre-trained CNN model, let's say, right? And you take the so FC7 basically says that you have the CNN model. There are convolutional layers, and then there are fully connected layers. And you take the seventh fully connected layer in the CNN, right? Which is some deep level of fully connected layer, which has very few number of dimensions. So you take that output, seventh fully connected layer in the CNN, and you use that as an embedding that describes the image, right? And the question is, how do you pass this embedding into the captioning model, right? Because your captioning model is going to be something similar to the RNNs that we saw earlier, right? Because it has to generate a sentence in word by word, and somehow you have to give that captioning model the information about the input image as well. So the question is, how do you pass that information?
Hello.
Uh, yes,
Uh, sir, I have a question.
yes,
Uh, like in this image caption generation problem, we take that CNN model image zero, and we go on ahead with the caption generation. So while we do the back propagation,
yeah.
we update the weights for the CNN data set or not? Because in the video, sir was saying that by the people like practically we do not do it like that and it's not that right?
Yeah, uh, so you can do it, right? Which is, I think, what the professor was trying to say, that you can actually do, you can actually train or rather update the weights of the CNN model as well, but it is typically not required, right? So for practical purposes, what you would typically do is that you will not train the CNN, right? You let the CNN be, right? So it's like a model that has been given to you by someone else, right? And then you trust that person, that this person has developed a model that gives me a very good abstract representation of what is there in the image within like a small uh, dimension vector, right? And then you use that to generate your output. And the other reason why you would not train the CNN model is that the base CNN model, out which you are getting the pre-trained CNN model, it is trained on maybe millions and millions of images, right? So it has a very good, it was trained on a very good data set where there are millions of images. Uh, so it learns the characteristics of all kinds of images, right? But the captioning data set that you are trying to learn your captioning model for, right? So you would have a captioning data set where you have an image and then you have associated with it, you have a caption, right? And you're trying to learn how to generate those captions. Your captioning data set is most likely going to be very, very small compared to the original image data set on which that CNN was trained, right? So when you re-update the CNN weights based on your very small captioning dataset, the CNN weights can get biased towards your dataset, right? And that will be a problem, right? Because when you go outside of your training distribution, that could cause a problem, right? Because essentially the CNN was supposed to learn a very wide range of uh, image data, right? And it has learned that, and then you are basically messing it up with a small amount of data that you have. So yeah, so what uh, you know I would say, what professor would have said in the video is broadly correct, right? Obviously, uh, you can of course train the CNN, but typically it is not done for both practical and pragmatic reasons, right? Yeah. So yeah, I think so. At least you have seen what and one part of it. Uh, the answer is that you can do both of these uh, ways, right? So you can set S0 as FC7, which is like S0 is the first input into your RNN model. Uh, Alternatively, you can also feed it to every as an input to every SOT, right? You can concatenate it to every uh, point of every state, or you can add it to uh, every time step, things, whatever you right. Essentially, what it does is that you know essentially what this does is that when you set S0 equal to this image embedding, what you're doing is you are you are initializing your state in some way, right? So you're initializing your state based on what is the image, and then you are no longer enforcing or reinforcing that information into your model, right? Whereas the second part is you are continuously, constantly reinforcing the information from the image into your model to make predictions, right? And uh, there is no like way to predict which of these will give you better results, right? So sometimes one will give better results, sometimes the other will give better results. It's kind of like I said, like uh, basically it's an empirical kind of thing. You try different architectures out based on your intuition, and you adopt whatever architecture gives you the kind of optimal best results, right? So yeah, so you can do both of this, right? The second thing that I have over here, this has a very nice analogy to something called units in image generation, right? Or image like conditional GANs, things of that nature. So this constant reinforcement of the input is something that that is very commonly used in image, right? So when you are basically when you basically change the image, one type of image from change an image from one type to another type, right? You go through this unit architecture where you reduce the dimensions of the image to increase the dimensions of the image again, and there are skip connections connecting, you know, images of the same dimension in the inputs, in the encoding side and the decoding side, right? And it constantly reinforces basically what was the information that was present in the input, right? So this is something kind of is more commonly used in image generation models, right? So here we have encoder-decoder models. So yeah, so we have a task basically, right? So we have an image, uh, similar, it is similar to the previous example, but little simpler. But so we have a image and we have an associated question, right? So image-based question answer. So we have an image as one part of the input and a question, which is a string of text, as the other part of the input. The expected output is a one-word answer, right, from a known text box, right? So you have already answer options available to you beforehand, right? And train your model to kind of predict the correct answer, right? So it just has to predict one word, right? So question here is, how do we plan for a problem like this? What kind of encoder and decoder architectures do we need? Okay. Yeah. So yeah, so A is in fact correct answer, right? So uh, we basically, the way to understand is basically to break it into all the component parts, right? The constituent parts, uh, and figure out what is required, right? So for the input side, you have two parts essentially. You have one is an image, and you have another which is sentence, right? A question. Right? So the way you process a image with CNN, right? So use convolutional network to process the image, generate a abstract representation of the image, right, which you can also call an embedding of the image. And the way you process a question, which is a string of which is a stream of text, is that you use a RNN. Of course, you could use transformer as well, right? No one is stopping you, but for now, let's stick to RNN. That's the options that we have over here. So so you use an RNN to process uh, use an RNN to process the question, you generate a abstract representation of the question, right? Because RNN remembers the history that goes into it, all kinds of things. So that gives you basically the encoder part. So you have CNN, RNN, and finally you concatenate both of those vectors together. You will have a representation that contains information from both the image and the question, right? All that remains now is how do we generate the output, right? So the decoder part, in this case, the decoder part is very simple because all you have to do is generate a one-word answer from a known corpus, right? Known vocabulary, and the way you generate a one-word answer versus basically just a normal feed-forward, right? So you just have to predict one particular probability distribution over the vocabulary, and whatever is the highest probability distribution, that is your answer. And of course, you don't need anything super complicated for it, right? You don't need an RNA, just need a simple feed-forward network that is good enough. Right? So, yeah, so together, kind of summarizing what I said, image, process it through a CNN, generate an encoding for the question, process it through RNN, generate for the question, concatenate them together, uh, pass it into a fully connected, neural network, give your output. Right? So this is once again another encoder-decoder type of model, right? Uh, Here you are previously the one prior to the previous question was about captioning an image. Now we are trying to, let's say, caption uh, video, right? And of course, output side, we know exactly what is needed, right? So on the output side, obviously, a recurrent neural network question is what you need input side, right? How do you encode? How do you encode a video such a way that you can generate caption out of it, right? Uh, okay, so here basically what you need, right, is some way to uh, both. So you want to process the individual frames as well, right? Because video is nothing but a sequence of frames, right, that you get one after the other. So you have to process the individual frames, uh, which of course will require a convolutional neural network, That's what you use to process images. And additionally, what you also want to do is somehow understand the relation between successive frames, right? So you need to encode the history information of these frames as well, right? And the way you do it is through a recurrent neural, right? So the answer to this question basically involves putting together both of these uh, aspects, right? So, and the way you do it is that you have a CNN to process each frame, right? So you use the CNN to process frames one at a time, and then the CNN generates an output which you use as an embedding in an RNN, right? So the way you describe it is an RNN of CNN, right? So you have CNNs which kind of act as the embedding layer and generates a abstract representation of the frame, and then that abstract representation of the frame goes into an RNN which accumulates the historical information and generates an abstract representation of the entire video, right? Which it tries to do, and that then you can further give into like a caption generating RNN or something like that, right? So yeah, so what you need here is RNN of CNNs, right? And the way you think about this is that typically when you have an RNN, right? When you have an RNN, you have a embedding layer which converts this raw text into these dense vectors, right? So in this case, for a video, just uh, just replace that embedding layer, right, with a CNN, right? So CNN is now your embedding layer that takes an image and generates a dense vector that is a representation of the information present in the image, right? And then this dense vector is now your embedding of that current frame, and you can use it however you want, right? So after this embedding, image embedding has been generated, you can use it typically. There is no difference in how you use that compared to like a typical RNN case, right? So yeah, so here is like the written explanation. So the video is nothing but a sequence of image frames. Then the way you encode videos is you have a CNN that processes each frame, and then the abstract representation is input into an RNN processes and the video together, or at least it tries to do that. So what you would call it is a recurrent neural network of CNN layers. RNN CNNs. Okay, so uh, so in this part we will only see like a very brief kind of introduction into attention. I will go into somewhat more detail uh, when after finishing these questions. I think this is in fact the last question. Yeah. So yeah, so this is so this question is the introduction to attention, right? Single head attention, multi head attention, whatever. So I think the basic, yeah, basic, the base technique is called self attention, right? So that was the technique presented by the original paper. The name of the paper, the name of the original paper is Attention is All You Need. Came out of Google, I think. Originally, so the original idea behind that paper was to make better language translation models, and then people found out that these attention models scale very well and they are highly parallelizable, right? And they can, then at some point GPT-2 came out uh, and it was quite revolutionary, right? So yeah, so that's like brief overview. See what it does. The question here is that suppose you know that only one of the words seen so far, right? So you have attention, you have this idea as a context, right? So only one of the words that is present in the past context is important. if that is the case, then it is sufficient to feed only that important word as input to the timestamp, right? So, you know, that is the most significant output input from past. But but that is not always the case, right? In case where that some more words are important, the question is, how can this be handled? In general, basically, what happens is that let's say you have n past inputs, right? You generate a like a probability distribution over those n past inputs, right? And you try to figure out which of the words are uh, more important and which of the words are less important, right? Of the words that have come uh, in the past so far. So the question is, how do you handle this case, right? And the reason, of course, the reason as to why you have to do it like this, of course, is that obviously you have to train this model, and in order to train a model, it has to be differentiable. It has to be with nice properties. Right? So it should be able to do gradient descent, which you can't do if within the highest probability output or something. Right? So based on all of this discussion, I think it should be fairly straightforward to answer this question. Right? I'll just give like a minute. We'll discuss the solution. Yeah. So obviously, the way you do it is through a weighted sum of the important inputs. In fact, the way you do it is through a weighted sum of all inputs, right? And the weights that you generate basically are represent this the so-called importance, right? And uh, we will see just in a few minutes how how this how this importance is basically uh, quantified, right? Because you have to generate some quantity, right? Some number that represents this importance, right? And based on that uh, value, you have to do the weighted sum, right? So yeah, so what you do is you weigh them by the relative importance uh, and generate the next vector. And this, in fact, like I said, is the basic idea behind attention, behind rather basic idea behind self-attention, right? So, so that's the end of questions. Here, so yeah, so now brief uh, introduction into transformers, right, and self-attention. So self-attention, attention is one thing, transformer network is one thing. Uh, this paper, famous attention is all you need. Extremely famous paper. Uh, Kicked off this phrase, right, or this current generation of neural networks that use transformer architectures. The basic idea here is actually very simple, right? This is the equation, $1 million equation. In fact, maybe it is $1 billion equation. And this encapsulates everything that is happening here, right? So basically, attention is generated uh, through these three things, right? So there is Q, K, and V. So these are vectors, right? So if you think about it, basically uh, when you have a context length of n, each of these is a vector, let's say of size d, right? D-dimensional vectors, uh, n by d. So it's an n by d matrix, right? You have n inputs uh, in time that you have passed into your network, into your attention module. You generate so n by d matrix of query key and value, right? And each of those vectors, right? So basically, query of some uh, time t in n, right? So that is one vector, right? And the way you interpret it is that query is basically asking something about the current uh, time step, right? So it is generating something like a question about the input at the current time step, or whatever at the t time step where we're looking at. And then what you're doing is that you have generated all of these key values, right? So these key vectors, uh, which also have been generated for all the time steps, right? And you are checking the cosine similarity between the query and the key, right? For all the time steps. So that is what is happening here. So when you do Q times Q transpose, uh, essentially what you're doing is that you are computing the inner product between certain query and every key, right? And then you're repeating this for every query that is here, right? And what it generates is an n by n matrix, right? An n by n matrix uh, these uh, cosine similarity or inner product values, right? And then what you do is you apply softmax on it, right? Which is very important. So softmax basically normalizes the relative so-called importance of uh, each of those key positions uh, for any given query, right? So softmax normalizes it, and then you multiply this whole thing with the value, which is another kind of matrix of n by t dimensions, and this is your attention output, right? And the way to this transformer model is that you add this attention output to the input that went into it, right? So that you can see that here. Uh, yeah, so you have an input that goes into this so-called masked multi-head attention, right? And you will see what is meant by multi-head and what is meant by masking, right? So it goes into so this is your encoding. Uh, yeah, so originally this was like conceptualized as a encoder-decoder model, right? But we can concentrate on any one of these parts, right? So yeah, so you have your encoder that goes into your attention, right? So you have your embedding, input embedding plus positional embedding that goes into your multi-head attention, and then output of the multi-head attention goes into this add plus norm layer. Right? So you have to, and what you add to it, you add the input, right? So essentially what you're doing is that you have, if you think of all of the inputs, input embedding as vectors in some high dimensional space, what you're doing is you are computing of the amount of uh, transformation or addition. You're computing the delta vector for each of those vectors, right? So basically, which direction you want the vector to turn towards, right? Which direction you want it to go towards, and you generate these delta vectors out of your multi-head attention block. Then you add those delta vectors to your input vectors, and your vector direction has not changed, right? Vector direction, vector magnitude, everything has not changed. So that's what this is doing, and that's why it is called as a transformer model, transformer architecture, because essentially what it is doing is that it is transforming the vectors from one orientation and magnitude to some other orientation and magnitude. And basically the transformations are mapping semantic meaning of words, of the words, right? And it is imbuing the semantic meaning of the past words into the meaning that is being generated by the current word, right? So that's essentially what it is. It is transforming the meaning of certain input, right? You can think of it in that sense as well. So yeah, so this is the attention clock in, in attention. Yeah, so this is multi-head attention. This is single-head attention, right? And basically, uh, like I said, we have this Q, K, and V matrices that are generated by simple linear linear right? And Q and K go into this matrix multiplication, right? And then there is a masking operation, right? And masking is very important for certain use cases, and it is not important, not required for certain other use cases. Masking is required when you are trying to uh, predict the next word given the history, right? So if you are trying like an uh, auto-regressive generative model, in that case, you would require this masking, right? For certain other use cases, for example, like a language translation, you would typically not use masking because the position of, or rather, the order in which uh, parts of speech appear in different languages is different, right? So, you know, uh, how subject verb agreement and all of those grammatical rules are different in different languages, right? So when you're translating from one language to another language, it helps to have the entire kind of sentence, right? Both past and future, right? And that basically helps you to generate the most accurate translation possible. So yeah, so you have scaling mask, masking, softmax, right? And uh, multi-head is nothing, you know, nothing special. Essentially, what you're doing is you're taking this single head attention layer and you are running it in parallel, right? You are running multiple of them in parallel using using different V, K, and Q values, right? So you'll have different weight matrices generating value key and query vectors for each head of attention, and then all of them go into this skill dot product attention, right? So there will be, in this case, there are three heads, right? So there are three scale dot product uh, attentions, and output of these three dot product attentions are concatenated that you have linear layer that does a transformation, right? So this is broadly the architecture. Then head attention, addition plus normalization. Then you have feed forward layer, and again the same thing, right? So you again apply a shortcut connection and add the shortcut and then analyze it, and so on and so forth. And this architecture is broadly unchanged, even in the GPT-2 style networks, right? So we'll see that a little bit. Here, uh, somewhat better visualization is a book that explains how to build LLMs, right? And yeah, so here, like I said, you know, when you have when you have a language translation model, so let's say you're trying to translate from English to German, right? And if you try to do word by word translation, you know, this leads to errors, right? Because uh, obviously the way you speak German, the language rules are different compared to the way language rules are constructed for English, right? Yes, yeah, you can see, can you need help, right? So you have both of the subjects together, then the word comes afterwards, whereas in English you will put the word in between, between you and me. So in this case, right, what is happening is that, you know, past and present kind of intermix together, because the rules of language are different in different languages, right? The rules of grammar are different. And in this case, you would typically not use a you would typically not use a masking layer, right? Okay. Whereas uh, whereas in autoregressive kind of GPT architecture, you would use this. Right? So see, uh, yeah. So you have something like this, right? And essentially, what you do is, so your every input step, right? Every input vector is is converted into some embedding, right? So this is a broad understanding. So every input word is converted to some embedding representation, and then the next step output is a weighted sum of all of these embedding vectors, right? So this is what we saw in the last question as well, right? So what you have seen, uh, essentially, yeah, have all of these embedding, uh, all of these attention weights, right? You weigh the importance, and then by adding them all up, you get your, right? So very attention. Mm, yes. So so you generate yeah. So basically, this uh, figure kind of explains best what happens, right? So essentially, you have uh, this. You can imagine this is the sentence, right? This is the context that you have been provided, and there are 2, 3, 4, 5, 6. There are 6 words here, right? And correspondingly, you can compute the attention, right, for every word with every other word that is present, right? So let's say you're computing, you know, how you would like to transform the second vector, right? And so this is your journey. You would generate a query based on this journey, right? And then you would multiply that query with the key for your, you would multiply that with the key for journey, the key for start with one and step, right? So you multiply the query for journey with the keys corresponding to all of these uh, words, right, in your context. And then you apply a, what do you apply? You apply a softmax, right? And softmax basically generates probability distribution uh, over all of the over your entire context, right? And this is the case where you don't have masking, right? So the probability distribution is basically saying that the most important words are these two, right? Journey and starts. Journey, of course, is the word itself. Uh, and the third most important word is step, right? And based on these weights, you would apply, you perform a weighted sum of the embedding of all of these vectors, and that will tell you how your second uh, your journey vector has to be transformed for the next layer, right? So this is broadly how self-attention works, right? So you generate this n by n uh, matrix. Of course, practical inference use cases, you typically don't generate the entire matrix, right? So let's see, right? So um, yeah, so like I said, uh, for every input, you have a query, right? So you have a query generating weight, you have a key generating weight, and you have a value generating weight, right? So it generates query, generates key, generates value for each of these, right? So this is x2, the second input, it generates query 2, key 2, value 2, so on, right? So x1, key 1, k1, v1 to xt, kt, vt, right? And then these queues are basically multiplied against all of these queries, right? So you perform inner product with the queue and all of these queries, and you generate that one row, and then you apply softmax vector, right? So broadly speaking, uh, yeah. So this is what happens, right? So this is generating the weights, the unscaled attention weights for the second row, right? And because it is the second row, we're going to use query 2, right, which is this one, and you use perform inner product of this query with all the keys that are present in your context. Query 2 times key 1, this generates W to 1, right? Second row, first column. Q2 K2 generates Q2, and so on, divided by 2, right? So this is our Q times K transpose operation. Then uh, we generate the normalized attention weight by using softmax, right? So you apply softmax on all of these things, uh, generate normalized attention weights. All of these together will add up to 1, right? And then finally, what you do is you multiply the value at each time step uh, in your context with the corresponding attention weight, right? And then you do a weighted sum of all of it. Like v1 by attention to 1, generate multiply v2 by attention to 2, vt by attention to t. Add all of this up, get context vector z2, which is the context vector for the second time step in your context, right? And this is broadly speaking, right? Um, yeah, and see some code. Well, please code. Yeah, but because before we go into the code, uh, you clearly, but yeah, so far, we have not talked about this because the masking, see the masking there. Yeah. So this is what is meant by masking, right? So without masking, your attention layer kind of looks like this, right? Uh, with masking, your attention layer look like this. And the idea behind masking basically is that you don't want the future words to affect the prediction of the current word, right? So here, for the first time step, right, you are trying to predict the second word, and uh, basically, if you allow the model to see the second word, that in this case, what you are actually training is a generative pre-trained model, right? So when you're training in a generative model kind of way and not in language translation kind of way, what you should do is, you can't let the model see what is the second word when it is trying to predict the second word, right? So for predicting the second word, it can only see up to the first word. For predicting uh, the third word, it gets see first and second words. For predicting the fourth word, it can see first three words, like 1, 2, and 3. For predicting the fifth word, you can see four words and so on, right? So basically, this entire part, this upper triangle part of this attention matrix has to become 0, right? So it can only have non-zero values in the lower triangle part, right? And that is applied. So this step is typically applied before doing softmax, because if you do it after softmax, then your probability distribution feature will be broken. So you basically apply softmax only on the inputs that are available to you. And one of the ways that you can do this is basically by making the attention values at all of these red cells to be like negative infinity or some very large negative value. Essentially, what it will do is that e to the power of whatever that value is will become 0, and it will not affect your softmax computation. Right? So yeah, so this is masking. Right? See some code self-attention. Code basically looks something like this. Right? Very simple uh, in PyTorch. So this is the causal attention. This is attention model without uh, multi-head, right? And you can see here there are three parameters: query, key, and value weights, right? There are three main sets of parameters, and then the way you compute key as uh, w key of x, right? And all of these w query, w key, and w value are linear layers, right? So these are typical, simple, fully connected network kind of layers. So like key equals to self dot w key of x, queries is self w query, then value is self dot of query value of x. Then attention scores is nothing but queries times key transpose, right? To transpose the transpose here. So the x that we get in has this shape batch size by context length by embedding size. So we transpose the context length and embedding size dimensions, right? So it becomes embedding size by context length um, in the key transpose. And queries is of course context length by embedding size. So the embedding size gets absorbed in between, and you get context length by context length, right? Which is what we had seen in the text as well. So you do this q times query transpose, uh, and you generate this mask fill. So this is your masking operation, right? Uh, So yeah, so you have your masking operation. So you have your masking operation. Masking is nothing but triangle upper, right? With length, diagonal equals 1. So apply your mask on the attention scores, then you apply partial softmax on your masked attention, right? This generates your attention weights, and then finally, after applying dropout, you just do attention weights times value, right? So this is final weight with multiplying the value vectors with the attention weights and generating the weighted sum of the value vectors. This gives you the context, right? And multi-head is uh, the same, broadly the same thing, but slight difference in the sense that uh, basically you have this idea that T out, typically what you do is T out, right? Yeah, yeah, so yeah, so you have this concept of head dimension, right? Which is the dimension of each head in your multi-head attention, uh, and basically you are trying to do it parallelly for each head, right? And of course, you don't actually do it parallelly because matrix multiplications are more efficient if you perform like large matrix multiplication. Uh, so the way you do it is uh, do some interesting shaping stuff, right? So have your key. So you generate your key query and value, right? Based on doing T out. Uh, then key is originally of this shape, right? So the key that you generate is of shape B, batch size num tokens by T out. You change this to B times num tokens num head dimension, right? So you split this T out dimension into num heads by head dimension, right? And then you do the same thing to the value as well. So you split the value into num heads by head dimension, and then you transpose the key, right? So you transpose 1 and 2, which is num tokens and num heads. So num heads comes first, comes here, num tokens comes here, then head dimensions comes here. You do the same thing to the queries, do the same thing to the value as well, right? And then when you uh, multiply this into this matrix multiplication, you do queries times keyword transpose with 2 3, right? So your key had this num heads by head dimensions. You swap these head dimensions, right? So get the output that you get out of this is num heads by num tokens square, right? And this is exactly equivalent to doing everything, to doing multiple heads in parallel, right? Essentially, you get parallel computation of num heads. Right. Then whatever masking stuff, that's right. So this is what multi-head attention looks like. Just briefly touch upon the architecture of a full GPT model as well. Uh, yeah, so the GPT model kind of looks like this, right? It's very simple, but we have a certain building blocks. You use certain building blocks here. So first thing that you do is uh, embeddings, right? So you apply token embeddings, right, which is your word embeddings, and you have something additional here which you have not used in, which is actually not required for typically not required for RNN LSTM kind of architectures, which is positional embeddings, right? And the reason you need this for transformers is because the transformers by itself cannot distinguish uh, if a word is present in if the same word is present at different locations in past context, right? So if the same word is present in different locations, it will generate same attention score for both of those cases. You don't use some kind of positional embedding, so you have to add a positional embedding. So yeah, so you add token and position embeddings, uh, apply dropout. So then there is this transformer blocks. See, right? So transformer blocks contains one multi-head attention, which you have already seen, and one feed-forward uh, layer, right? And the way you do it is apply the normalization layer, then apply the attention layer, right? And then you do this shortcut, right? So you add the shortcut, and then you have a feed-forward block where you do the same thing, apply the normalization, apply the feed-forward, then again add the shortcut, return the output, return the added. And feed forward is nothing special. It's just a typical NN linear. And the only thing here is that instead of ReLU, use something called as get GELE in some uh, continuous uh, approximation of ReLU. It is kind of similar to the exponential linear unit. So yeah, so this is literally what is there. All that is really there. Uh, and very simple, right? So there are a bunch of transformer blocks. So you have embeddings, positional, and word. Then there is a number of transformer blocks, which includes multi-head attention, followed by feed-forward layer, and then out of the transformer blocks, you just have a outhead, which is a linear projection, right? And that is literally all that there. And the way that thing, things have been developing over the past years is that this model has been scaled more and more, right? So this is the GPT-2 scaling, right? And yeah, and then basically you can scale number of heads, how big your embedding dimension is, how many layers you're going to have, right? And so on and so forth until uh, yeah, this is small config, medium, large. So yeah, so that's a brief introduction into GPT architecture. Like I said, but I think so. With that, we are done. If anyone, either of you have a question, you can ask right now. Otherwise, this class is over. You can end the call. Okay. There doesn't seem to be any further questions. Yes.